presentation about a lab I have done. First, I will have a quick introduction of this video, then talk about important physics concepts that will be used throughout the video. Also, I will provide a brief preview of the result of the experiment, then I will talk about the experiment details and the overall experiment in detail. Afterwards, I will talk about the possible sources of error and answer questions on what if and what does it mean. The purpose of this lab is to determine the motion of a spaceship orbiting the black hole using the calculated mass of the black hole. The main concept introduced in this lab is the Newton's second law of motion. According to Newton's second law of motion, the acceleration of an object is directly proportional to the net force acting on it. There are four main formulas that were used in this lab. The first one is the velocity update formula using Newton's second law of motion, and the second one is the position update formula. With the velocity update formula, the change in velocity will be calculated, which will be used in the position update formula to predict the position. The next formula used is the gravitational force, which is to calculate the net force acting on the planet and the spaceship. Also, the net force can be calculated by adding parallel and perpendicular components of the net force. This is the brief preview of the trajectory motion of a spaceship. The system is the spaceship and the surrounding is black hole and planets. In this lab, one assumption made is that the only forces applied are gravitational forces between objects. The initial condition is that the mass of the star is 2 times 10 to the power of 30 kilograms. This is the code to calculate the mass of the black hole. I set the initial and final momentum using the mass and the velocity. Then I calculated the change in momentum over time, which is the same as the net force, and I found the parallel and perpendicular components of the net force. With the distance between the star and the black hole, mass of the star, and the gravitational force between the star and the black hole, I calculated the mass of the black hole. There were a total of 445 values calculated for the mass of the black hole, so I calculated the average of these values to find the accurate numerical value for the mass of the mass of the black hole. Part 2 was about the trajectory motion of a spaceship. I found that with the initial speed vector of the spaceship, negative 7 times 10 to the power of 6, 9 times 10 to the power of 6, and 0, the spaceship can go close to the black hole and escape from it. I tried to find the net force acting on the planet and the spaceship. The forces that need to be considered were gravitational forces. Lastly, I updated the velocity vector first using the velocity update formula, and I updated the position using the position update formula. This is the motion of the planet and the spaceship orbiting the black hole. The motion of the spaceship is indicated in purple. There are two possible sources of error. First, when calculating the mass of the black hole, the average mass of black hole could have been calculated more accurately by running a program for a longer time. Also, with part 2, the time interval was too short. However, these errors do not significantly affect the lab results. Furthermore, there are not many sources of error since the lab was done with a computational model. There are two questions that can be addressed for this lab. First, how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. To answer the question, it is important to know that there are two ways to calculate the net force. The first way is to find the sum of parallel and perpendicular components of the net force. The other way is to calculate the change in momentum over change in time, which is the same as the rate of change of momentum, and the final momentum and initial momentum are the sum of parallel and perpendicular components of the corresponding state of momentum. The second question is, what initial velocity would your spaceship need to have in order to enter into some kind of orbit around the black hole? Your spaceship should still not crash into the black hole nor crash into the planet. The orbit colored in blue indicates the motion of the planet. Therefore, I thought if the x component and the y component of the speed of the spaceship is greater than the corresponding component of the speed of the planets, then the spaceship can orbit the black hole outside the planets. Therefore, I set the x component of the speed to 100 and y component to 10 million. And the motion of this spaceship is indicated in purple on the diagram. Thank you for listening to my presentation, and this was Esther.